Hi, my name is Jason Rockwell, and this is my video on the Spearman Rank test, and this is for elementary statistics at University of Tennessee Martin. Spring semester, spring now, yeah, it's spring. So without any further ado, I'm going to go ahead and minimize this window right here, and I'm going to show you. Obviously going to be doing it in Excel because, frankly, I think it's a great tool. Not that I have a problem with SPSS, I'm just more used to and familiar to with Excel. So very simply, the first thing we need to do is I have two sets of data right here that I'm going to be comparing the correlation to. And what I'm going to do the first thing, obviously, and I prepare some data over to the side over here that you can't see. But the first thing I'm going to do is I have to rank this data. So the first column I'm going to rank is going to be that A column right there. And as you can see, obviously, the lowest rank is going to be that highest. So a 13 is ranked as a 1. A 12, 2, 11, 3, so on and so forth as I go lower. All right, I'm going to do the same thing with that B column, where I have rank already prepared over here just for the sake of time. If I can click on it. Okay. So here you can see I've also ranked this B column. So rank A for this column, rank B for this column. The next step in the Spearman rank is going to be to go ahead and get the difference of these two ranks and bring it all across. And of course, as you can guess, I've already prepared that over on a separate spreadsheet over here on the side. So as with anything else, it's just, this subtract that equals that, just a basic difference. So as you can see, 10 take away 6 obviously is going to be 4, so on and so forth. Okay. All right, now the next step in the test is going to be the difference squared. So we need to go ahead and square each of these differences in their order. So as you already know, I have it prepared. I'm going to copy it. I'm going to paste it right over here. All right, so obviously 4 squared is 16, so on and so forth. And the next step, as we push it along right here, is going to be to get the sigma or the sum of all of this. And I can tell you just from rehearsing this a couple times, I know this is going to be 146. And just so I don't forget that number, because I know I'll need it later, I'm just going to go ahead and highlight that. All right, now we actually get into the computations, or actually figuring out the formulas of some of this. So in this step, the first thing we need to do is we need to go ahead and multiply this 146, which is the sigma of the differences squared, by 6. So very simply, if I was going to do that, I'd go 6 times, I'm going to come over here to F12, all right, which I already know is the sigma squared. All right, and that's going to give me 876, an important data point that I want to go ahead and just keep in mind. All right, and the next formula that we're going to have to go ahead and compute as a part of this the Spearman rank is n being the total number of data points, and then n again, or times n squared, and then subtracting 1. I really butchered that, didn't I? Here we go. N squared subtracting 1. All right. So in order to do that, what we need to do is know we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points here across. So we're going to go 10. Oh, I'm sorry. Equals 10, and all those we're multiplying. All right. Then we do our PEMDAS, our order of operations. 10 again, instead of just going squared, we're just going to do times 10, because 10 times 10 is 10 squared. Times 10, and then subtract 1. And luckily, Excel does all our orders of operations for us. And that's going to go ahead and give us that 990. The next step that we need to go ahead and execute in our Spearman rank is we're going to go ahead and need to pretty much divide this and this on our way to our correlation. And then once we achieve that number, we need to subtract it from 1 in order to see what the strength of our correlation is between these data sets. So the first thing we're going to do is we're going to go ahead and equals, and we're going to go F6 divided, or 876 divided by 990. All right, and that gives us 0.88844444. We know we need to subtract that from 1. Subtract that, and then go ahead and throw that data set or that number in there. And it gives us 1.1 or 0.1151. And as we can see from this being the conclusion of our Spearman rank, this is a fairly low or extremely low actually correlation between these two data sets as it comes. So that is my presentation of the Spearman rank correlation coefficient test. Let me know if you have any questions. Thank you.
Hi, my name is Abbie McClure, and I'm going to show you today what the Wilcoxon Rank Sum Test is and how to use it in order to solve a problem. In today's lesson, we are going to find out exactly what the Wilcoxon Rank Sum Test is, what it's used for, the steps in conducting a Wilcox Rank Sum Test, and we're going to get to solve an example on our own. So let's get started. In this test, the values of data for both samples are combined and then ranked. If the null hypothesis is true, which means that there is no difference in the population distributions, then the values in each sample should be ranked approximately the same. When the ranks are summed for each sample, the sum should be about equal and the null hypothesis will not be rejected. If there is no difference or any large difference in the sums of the ranks, then the distributions are not identical and the null hypothesis will be rejected. The Wilcoxon Rank Sum Test is a test that's used to test independent samples and compare distributions. It's very important to realize that this test is only used for independent samples. When testing dependent samples, you will use a similar test known as the Wilcoxon Signed Rank Test. Here are the steps for the Wilcoxon Rank Sum Test. First, we want to state the hypothesis and identify the claim. Secondly, we want to find the critical value. And thirdly, we want to compute the test value. Combine the data from the two samples, arrange the data in order, and rank each value. Add together the ranks of the group with the smaller sample size. If both groups happen to have the same sample size, either one can be used, as you'll see later. On this slide, you will see that here are the formulas you will need in order to compute the test value. We will talk all about these formulas later in the video. The fourth step in the test is to make your decision, and the final step is to summarize your results. Using what we've learned, let's try an example. Two independent samples of men and women are selected, and the time in minutes it takes each individual to complete a physical challenge is recorded as shown in the table below. At a level of significance at 0.05, is there a difference in the time it takes the individuals to complete the challenge? Using the steps earlier, let's solve a problem. Step 1. State the hypothesis and identify the claim. Our null hypothesis is that there is no difference in the times it takes the individuals to complete the challenge. Our alternative hypothesis is that there is a difference in the time it takes the individuals to complete the challenge. This is our claim. Step 2. Find the critical values. Since we know the level of significance is 0.05 and that this test is a two-tailed test, I used Table E in the back of my textbook to find the z-values. Those z-values are positive 1.96 and negative 1.96. Now we're ready to compute the test value. First, I combine the data from the two samples, arrange the combined data in order, and rank each value. Don't forget to indicate the groups. So in this case, men and women. It's very important that we note that. Next, I'm going to sum the ranks or add up the ranks of the group with the smaller sample size. Just please note that if both groups have the same sample size, either one can be used. In this case, our sample sizes are the same, so we're going to be using the men. So we're going to see that R is going to be the sum of the ranks. So we're going to add 1 plus 2 plus 3 plus 4 plus 6 plus 7.5 plus 13 to give us 36.5. Let's continue computing the test value. We have to know R before we can get into this next step. We're going to basically substitute the numbers into the formulas to find our test value. Please note that N1 represents men and N2 represents the number of female. All we have to do now is simply enter in our data and compute, and we will find out that our test value is negative 2.05. We are now coming to the end of our test, so we want to make our decision. our decision is going to be to reject the null hypothesis since our test value of negative 2.05 is less than our critical value of negative 1.96. And our last thing is to summarize our results. We found out that there is enough evidence to support the claim that there is a difference in the times it takes the individuals to complete the challenge. Now you know the steps for the Wilcox Rank Sum test.
In today's tutorial, we are going over the Kruskal-Wallis test. It is a non-parametric test, also known as the H-test. This test is used when the populations are not normally distributed, when the population variances are equal, and we are in comparison of 3 or more means. The criteria for the Kruskal test is each sample size must be 5 or more. Some other important information we need to make note of is all data values are considered as a group. These data values are ranked, and then the test is always a right-tailed test. The significance of our test values that we find are, if the samples are from different populations, the sums of the ranks will be different, and the H value will be large. Therefore, the null hypotheses will be rejected if the H value is large enough. On the other hand, if the samples are from the same population, the sums of the ranks will be approximately the same, and the H value will be small. Therefore, the null hypotheses will not be rejected. The steps for conducting a Kruskal-Wallis test are as follows. Number 1, we state our hypotheses. Our first hypothesis is there is no difference between the values of the group. Our alternate hypothesis is there is a difference between the values of the group. Our second step is to find the critical values. In doing this, we use the table G for our values. The degrees of freedom are k minus 1, where k represents the number of groups. Number 3, we compute the test value. We arrange the data from the lowest to the highest value. Then we rank each value, and we be sure we keep our group identification close to these values. Next step is to find the sum of the ranks for each of the group. Then we substitute the values into the following formula. H equals 12 divided by N, which is their total number of data, times N plus 1. This is multiplied by our first total values divided by the total number in the group plus the total rank values of the second group divided by the total number in the second group, and this carries on through however many groups that we have. Number 4, we make the decision to either reject or not reject the null hypotheses, and number 5, we summarize our results. Our example. The University of Tennessee Success Center supervisor wants to see if the number of students who take advantage of the services provided by the disabilities offices are the same at 3 of the university sites. The data for the number of students is listed for the past 5 years below. At alpha equals 0.05, is there enough evidence to reject the supervisor's claim that the number of students is the same for the 3 centers? Number 1, we state our hypotheses. Our first hypothesis, there is no difference between the group of students. Our alternate hypothesis would be there is a difference between the groups of students. I do not have that on the screen, but make note of that. Number 2, we find our critical value. We have 3 groups, so k equals 3 minus 1, which means the critical value, we look for the number 2, the alpha level is 0.05. In table G, it gives us the critical value is 5.9191. The third step is to compute the test values. We've arranged all of the values into 3 different groups, the Martin campus, the Chattanooga campus, and the Memphis campus. The Martin campus has 193, 174, 170, 165, and 168 students that have taken advantage of the center's disability center in the past 5 years. The Chattanooga campus has 213, 200, 190, 200, 205. And the Memphis campus values are 280, 283, 270, 241, and 200. After we put the groups, then we're going to rank the data values. We start from the lowest, which is 165, would give us a number 1. The next is 168, number 2, 170, number 3. 174 is number 4. Then we look at Chattanooga's campus is 190 is our fifth value. Our sixth rank is 193. As you can see, 7, 8, and 9 are all 200. Therefore, we take 7, 8, 9, and we take those three values, ranked values, and we divide them by 3, and we come out with 8. So all three of the 200s get a value of 8. And doing this, then our next number would be 10, and that would be 205. Then we go to 213, which is ranked 11th. 241 is 12th. 270 is 13th, 283 is 14th, and 280 is 15th. As you can see, the ranks have been put in red and the totals are underneath for each different campus site. Martin campus has a total of 16 of their sums of their values. Chattanooga campus, the rank sums are 42. The Memphis campus, the rank sums are 62. Then we substitute these values into the formula. Therefore, we will have h equals 12 divided 15 times 16, and this value will be multiplied times 16 to the second power divided by 5, plus 42 to the second power divided by 5, plus 62 to the second power divided by 5, and this is subtracted by 3 times 16. When we work it out, we get h equals 0.05 times 1172.8. And this value is subtracted from 48. 48 is subtracted from this value. Therefore, we get a test value of 10.64. Our test value 10.64 is greater than our critical value of 5.991. Step 4 and 5 is to make a decision and summarize these results. We reject the null hypotheses. There is enough evidence to show a difference between the three groups. That ends our tutorial. Thank you for your time.
Hi, this is Jana and today we're going to talk about the sign test. The sign test is the simplest non-parametric test. It's the non-parametric equivalent to the t-test. And it's used when the conditions of normality cannot be met, when the distribution is not normal, distribution is not symmetrical, and that's when the sign test will be used, or any non-parametric is for the conditions of non-normalcy. So, to look at the sign test today, we're going to use this question for our example. And it just says, a researcher wants to test the effects of smartphones on the number of text messages sent by teenagers. The researcher wants to know if teenagers send more text messages when using smartphones compared to using non-smartphones. And to do this, data was collected from 20 teenagers. And these teenagers had a smartphone, and you can see here that their non-smartphone data was collected for text messages sent, and then their smartphone data for text messages sent. So now, let's look at our question. At an alpha level of 0.05, can the researcher conclude that smartphones affected the amount of text messages sent by teenagers? So our null hypothesis then would be there is no difference between the text sent, and then our alternative hypothesis would be that there was an increase in text messages sent. So now we're going to go over and look at our SPSS data. And you can see here, for time's sake, we have the data entered in already as column 1 is the non-smart phone user, and then the column 2 is the smartphone. And you'll have row 1 is participant 1, row 2 is participant 2, and so forth. So in order to run the sign test,
We have our data entered. We have adjusted in variable view the non-smart and smart so that we will know which one's which. Go back to data view. Now we're going to go to analyze. And once in analyze, we're going to go down to non-parametric. And in non-parametric, we're going to go to the related samples. No, I apologize. Legacy dialogues. And once in legacy, you're going to go over to the 2 related samples. And I have already added this in. However, we can remove that to show you exactly how to do that. So our test pairs is going to be comparing the non-smart to the smartphone. Now, we're also going to make sure here that Will Coxon is unchecked and that sign is checked. Now, I have went to the options and I have included descriptives and quartiles. And then on exact, I changed our confidence level to 95% to accommodate the 0.05 alpha level. So continue. Now we have it all set up and we're going to click OK. When we click OK, we will get our output. We look at our output here and we find our descriptives, number of samples, the mean, standard deviation, minimum, maximum, and where they fall. Okay? Now, on our sign test, we see that there were no negative differences. So, each student who had used a smartphone did send more text messages. They were all positive. And then we get to the important part here on our test statistics, and you can see that all are 0.000. So if we were looking for a 0.05 significance level, these fall well under that, which means we will reject our null hypothesis, stating that there is no difference between the amount of text messages sent. And if we reject our null, we will accept our alternative hypothesis, which states that there is an increase in text messages sent. So, in conclusion today, it could be that you will never need a non-parametric test. You may never need to use the sign test to answer any of the research questions that you propose. On the other hand, you may find yourself dealing with some samples that may be very small or data that violate some of the important assumptions that underlie the parametric test, and you may find yourself using the sign test. And so I hope that this has helped to clear that up on how you use SPSS in order to run the sign test and exactly what the guidelines are for that. Thank you.